Hi, and welcome to Hardware Design. I'm going to talk a little bit today about an introduction to Perl, so covering some of the basic syntax and the basic data structures. This isn't meant as a sort of comprehensive instruction on how Perl works, and I expect that most of the people watching this have some experience with a programming language. This is meant as a make-up lecture for the course I'm teaching this semester, but maybe some other folks will find it helpful. So the reason to talk about Perl, mostly if you've been watching the other videos, is that we're using Perl to generate RTL, to generate Verilog. And so it ends up being a very powerful semantic in the sense that we can kind of concisely describe some things and have Perl elaborate out the Verilog that we mean. And avoid doing things like writing similar code over and over again, and build widgets that are a little more flexible than if we restricted ourselves to just the system Verilog or just the even older Verilog in VHDL. It also comes up a lot for tool flows. So this is often used to organize scripts that run, called various tools to perform designs. So I've used this in the past to run synthesis scripts or to run place and route scripts. I've way before that I used it to run some analog design analysis. It ends up being fairly useful for automating design flows, especially if you start to find that a lot of the time you're typing the same commands into the terminal over and over and over again. And the reason to use this over something like a bash script is that it's a little bit easier. It's a little bit easier to do some sort of data structure and file I/O work. But Bash and Make are also fairly common. The other thing that folks use this for is to collect data and analyze data. So in the past I've used this to crawl through the design database and pull out everybody's design reports, put it in a spreadsheet and give it to a manager. But along the way analyze some of that data so to find out if certain parts of the design are meeting their specifications. So it ends up being fairly useful. I will say that more and more folks are switching to Python. It has a lot to do with that younger younger computer scientists and younger electrical engineers will have seen more Python than Perl. And so as folks start to fill in those positions, they're going to write more Python to automate the flow. But if you work at a larger company, it is likely that you're going to be seeing scripts that are 10, 20 years old that have just been maintained over the years. And so it's good to be a little bit comfortable with Perl as well. But since we also use it for our design language, we're going to need it. That being said, I write both Perl and Python, and they're so I'm sure that this will be the first video that anybody comments on if I say that it's Perl and Python are more or less exactly the same. They're not that different from an abstract point of view. So let's start really simple. So there are roughly three data types in Perl. The first are scalars, right? My $A equals, some string. So this is, and the way to think of a scalar is that it holds one thing. Strings are a special case of scalars. My $B equals 22, so it can hold strings. No, we'll call these integers. My $C equals, it can hold floats. We could print those out. $A, $B, $C. So the way we just run it on the command line Perl, hopefully it's installed. So one difference to Python is that the print statements in Python, I think, implicitly add a new line, but in Perl, I don't think they do. They're maybe maybe we can do that. No, that's not a thing. So just make sure that you terminate with new lines so you get reasonable code. And you can see that inside of strings we can just refer to the scalars directly, and then that sort of works. There's some good behaviors to follow. It's generally a good idea to use strict. I have some other good things that are good to use. So we're just going to steal those for a second. It's also a good idea to use warnings and to set them all to fatal. And then to use diagnostics. So the first one is going to force Perl to have a strict interpretation of what you're doing. So if it's ambiguous on what you could mean, it's not going to try and guess by the context or guess, have a reasonable default. It's just going to immediately say, I'm sorry, I don't know what to do here. There are some warnings where it's clear what you want, but it's not quite in the right format. And so I generally turn these warnings into errors. These two things are a fairly good idea if you're working in a production environment, mostly because eventually somebody else will run your tool. And these things make sure that the hinkiness go away. And so, one option would be to turn warnings off and suppress them. The other approach is just to not allow warnings at all. This use diagnostics, what it does is if a warning does print, it'll print extra info. And so I found this useful, especially if this is your first intro to Perl, in sort of seeing what's going on. But I've also found that in general, even though I've been doing this like 15 years, it's fairly helpful to be able to just have a full plain English message saying what happened. All right. So those are our scalars. The fourth kind of scalar that I can have is not something that we'll spend too much time talking about, but I can have pointers. And I can actually print the pointer there. And so, it tells me that it's a pointer to a scalar, and this is the address that it's at. That's kind of fun. I think that's the /$D. I'm trying to remember how to dereference. So I think if we do $, yeah, so the dollar will dereference it. It appears to be one of the tricks. So we can do that. That probably doesn't seem too helpful since we've only talked about scalars. But sometimes what you find you want to do is to sort of move large data structures around, and pointers end up being a more convenient way to move data structures than it is to copy the data around. So just copying the pointer somewhere kind of helps. The second data type is an array. Oops, I'm mucking up my notes. All right. So the way that I declare an array is with the @ sign. And I can initialize it with these paren environments. And then generally all an array is a list of scalar values, or a list of values. And so I can print that as well. Though, to be honest, the print statement isn't that useful, because it doesn't do this nice thing where it prints out without lists. But we can see that we put string in there, and 1 and 0.5, and those appeared. So that sort of worked. If we wanted to access a specific value, a specific value, we would use these brackets, and we will do this. That won't work for reasons. All right. So that just printed A0 because we only did A0, but if we do $A0, it'll print the first element. So to access the first element of A, we'd write $A0. Now this A and this A are different A's. So this at is in the namespace for arrays, and this A is in the namespace for scalars, and so they don't collide, which can be very helpful if you mean to have things that sort of act as like this sort of scalar thing. So naturally, if you have a list or an array, you probably want to access it. So the easiest way to do that is a for each loop. There's going to be a loop variable, and then we give it the array to iterate over. So we're saying for each element $e in the array at A, execute this loop, and we'll write ourselves a little print statement here, and then we'll have another new line here to clean us up. Great. And we'll update A's definition. One, two, three. There we go. So now we have an array, 1, 2, 3. This worked through it, 1, 2, 3, and generally it's going to preserve the order. I think we can say something like sorted, and what sorted will do. This is probably not how this language works. Sort at A. And then in this case it's 1, 3, 2. So what sort does is it sorts the elements with some built-in comparator. And I think so there is a built-in string comparison. So you could actually say something like, is 1 greater than 3? Sorry, greater than. I guess not. So there is a built-in compare somewhere. Just not sure. It's been a long time since I've played around with it. So that's pretty helpful. If I wanted to know the length of an array, I can write print, and I can cast the array to a scalar, and that will give me the number. So scalar at A. So 3, so there are 3 things in it. If you, for some reason, need the loop indices, so for each my $I, and now what I'll do is I'll do 0 ... $pound A. $I goes to $A, $I. 0, 1, 2. So this returns the index of the last element. So in this case, the last index should be 2, which is what we got here. 0 ... $2 says give me the walk of integers from 0 to whatever this number is, including that number. So 0, 1, 2. And so this effectively becomes the list. There is a more traditional for my $I equals $0, $I less than scalar at a $I that works. So if you wanted to, if for some reason this wasn't sufficient, so one, if you were doing an interesting update here, so it wasn't by ones, but you were sort of walking around a little bit, that might make more sense. And again, it works like that. So if you're interested in adding elements to the array, push at A. The way to do that is with this. We'll do lazy print. So hopefully that works. I don't want to have to go. Yeah, so that's a problem. So that it turned this into a scalar in that context. So I have to write it like this. So concatenate assumes scalar ops, and so it'll cast it to scalar. So we have 1, 2, 3, awesome, good. So this is to push to tail. Similarly, if I'm interested in popping, I might write my $pop val equals pop at A. Boom, like that. And so what this will do is it will return tail value and remove it. So we added awesome and then we removed awesome. And these are generally the way that you would populate an array if you needed to, is using these push and pop semantics. You can imagine that since there's these tail accessors, the other thing that I would do is if I wanted to remove from the front, I would use shift at A. So I'll write, my dollar. So I'll write dollar pop val equals shift dollar A. This is return head value and remove it. So now we're at just 2, 3. And then if I wanted to put it back, I might unshift at A, and then I would put dollar pop val. So we put it back. Good. It's sort of a final note. What I would say is you probably want to look at splice. So the function splice. If you're interested in mucking with the middle of an array. And then let's see. Oh, the last one, I at B, is that every now and then you'll have 2 arrays and you'll want to put them together. And so the way that this works is that the push command actually is general in that the second argument can be an array. And so what it does is it appends the elements of B to A. So we can do our lazy print again. Yep, so 1, 2, 3, 5, 7, 8. Good. That's more or less how an array works. So the third type we'll use a lot is, still mucking up my notes, is a hash. So a hash always starts with a percent sign. If you've been doing a lot of advanced C programming or Python, this is just the same as a dictionary. And it is organized as key value pairs. So the syntax is key and then equals greater than a lot. So this is meant to be an arrow. So spam points to a lot, or Spanish points to Inquisition. 5 could point to yes. No could point to 2. So those are all reasonable things to say. And we could certainly ask it for a specific value. So that is something that you'll want to do a lot. So in this case, we can read out spam with the spam a lot. There's generally, in the same way that we'd be interested in iterating with our loops over here, we'd be interested in iterating over these. So what we might do is we could pick to iterate over keys. So we got the 4 keys, Spanish, no, 5, and spam. Notice that they are not the order that we put them in. So the order is not guaranteed. We could similarly put the sort keyword here if we wanted to guarantee an order. So now we got 5, no, spam, and Spanish. This is somewhat helpful if we want to sort by keys. If we're only interested in dealing with the values, we could write values %h. And that'll print out the values. So now we get 2, a lot, yes, and Inquisition. So if we delete the sort, I think the order should be similar. So 5 points to yes, no points to 2, Spanish, Inquisition, spam a lot. I don't know if that's guaranteed. In general, if you're interested in dealing with key value pairs, it's best to generally write something like this, where $H gets $key, and then this becomes $key arrow $8 $V. Let's add a new line for kicks. Boo. I forgot the package name. Yeah. Ooh, so we forgot something. You said use strict, so this is requires explicit package name. Did you forget on line 73? So this is line 73. So the issue is that square brackets are an array, curly brackets are hash. So there we go. No 2, spam a lot, 5 yes, Spanish Inquisition. Good. So that's generally how you deal with iterating over those things. Now, to add elements, you could always just create a new key, right? So we could say that $H, curry equals 3.14, and then print out what's going on. And so we've just added curry. So this is the way that you'd add elements. If you wanted to delete an element, you would just do the same thing. So I think it's delete. Yep. So we had curry for a bit, and then curry's gone because we deleted it. If you wanted to check if it exists, so let's add we'll say chicken and korma. All right. Just making sure I didn't have any typos. So we could ask questions like, is it defined? So we could say defined $D food. We'll say chicken. Print 1, otherwise print 0. We'll just print a new line here just to make sure our output's pretty. Then we all of a sudden started switching to D. Ooh, near the one. Uncaught exception. Syntax error is line 99. So the issue is that was a colon, not a semicolon. Good, so that's what 1. So chicken is defined. This is actually kind of the complicated way to write this. You can just write print defined. It should just work. Yeah, and it returns a 1. What you might be interested in is it defined or does it exist? So we'll say print exists. They're a little bit picky about semicolons. It'll only let you cheat on the last semicolon. So yeah, so it's defined and it exists. So if we wanted to define a under one, we could sort of say, well, goat, and then we give it the keyword undef. So it's not the string undef, it is the keyword undef. And we could play the same game again. We can ask about goats. And I think that if it's false, it returns an empty string instead of a 1. So it does exist, but it's just not defined. Good, good, good. So that's what the print 1, print 0 trick is for, was to make sure that we actually get the 0. But the empty string is just as good in most cases. So if we were interested in, say, building a new hash, what we might do, so something that comes up every now and then is you have, 2 hashes. And you're interested in generating a new hash. So we might go my %nh equals, I can join them with just using the built-in paren operator, so that will join them. And so then we'll grab this one, and then we just want to make sure that this says nh, good. And we tried to print an undefined value, so it's a little upset about our undef. So this is the danger of undefs. So we're gonna change goat to was undefined. Huh. So there's a bug in my issue, so it seems like there's some problem with what's going on here. So which one is it? So it's saying that the $V is an issue. So we're just going to be a skosh lazy. And we'll say $V. And then we'll say defined $HK, then $H, $K, and then we'll have the string O. And hopefully that solves our problem. Yeah. So the issue was that for some reason these were coming up as undefined in the declaration. So for some reason we did this version wrong. So let's try that. Or that. Or that. Forgot our semicolon there. So 1, 2, and 3 all ended up being undefined, which is interesting. So we must have done something a little bit hinky here. See if it needed white space. No? So this is a bit embarrassing, but it's not clear. Maybe we're gonna cheat a little bit. And what we're just gonna do is we're gonna do that. Interesting. So what happens if I swap this order? Does it? For some reason, this %D just is not, this statement is not working for some reason. Yeah. So what happens if we do this? Amazing. Oh. Die. Okay. So the issue is I changed this line, keys NH, but I left these as H. So that was the issue. Now it works. Good. So the issue is a typo here, and then I came up with 3 different ways to declare hashes while we were doing that. So that's fun. Let's see. So we did that. We put them together, and then we printed them out. I think the last thing to sort of say is that these can be deeply nested. So yeah. So this is a description of the design. I have a hash of registers, so every register has a name that we're using as a key, and then the value is a 2-element array with numbers in it. And then this is just a configuration telling me that it's read from bus or write to bus, which can be pretty helpful. or this is a traditional hash that is an operation table with opcodes in it. And then the really fancy one is this one. And this is written in a sort of hinky way. So you notice that if we use that parens, it just concatenates two arrays together. So what this is it's a hash. Each element in the hash is an array, so that's what this outer one. And then each element in the array is also an array. And then this QW syntax is a way to sort of do quoted arrays. So what you get back is from this would be a 2-element array with the first element being MAR under enable, and then the PC under select. And then we can go sort of crazy here on this and keep going all the way. And so this is the control logic for the hardware. It is just a table of the signals that get asserted on certain cycles, so I can build out the opcode table. So let's see, was there anything else to say about that? Nope, not too much. You may find that you do the same things over and over again, so I keep printing things out. So maybe when you do find that, find that you're doing that a lot, what you might do is write something like a subroutine. Actually what I'll do is my max, and the way that we get arguments is by doing an implicit shift. Return $A greater than $B, $A, $B. Great. Print my max 22 and 35. So we get 35 back. So what's happening is that the function myMax puts 22 and 35 in the array called @under. So we could actually take a peek at under. Ooh. It did not like that. Because I forgot a semicolon. So it's saying we got 22, 35, and 35. So the arguments were 22 and 35, and then we just printed the output. And so what's actually happening here is that this is really @under. And so we could say something like print I got scalar @under arguments. So I got 2 arguments and the answer was 35. And so if we keep adding things, 45, 67, 89, Thomas, right? It doesn't change anything other than that we've put more arguments in there. So that's one thing to keep an eye on. It also means that you can play neat games with some of these functions, right? So my max could be written in a way that it just accepts a list and always returns the max of that list instead of working on pairwise things. There's lots of fun to be had. So the last thing to talk about is how we might use these to generate hardware. And so we're going to go back to this microcode unit because it has examples of stuff that I do over and over again. So one of them is that if in keeping track in an array somewhere of what all of my signals are called, I can do kind of trivial declarations. So in this case, what I'm saying is, well, I know what my registers are, and most of my registers are going to have a value that is some wires that correspond to the actual current register value, wires that correspond to the next register value, and then a register enable. And then sometimes there's a register select. So instead of manually writing them all out, since I had the hash of registers anyway, I iterate over the hash and elaborate those lines out. So let's see. Genesis under synth, Ucode. Make gen module under name equals Ucode. Make clean. So now we could see what's going on in Genesis under synth Ucode. And what that gets elaborated out to are this long list of, well, PC, PC next, PC enable, PC select, T, T next, T enable, T read, temporary read, so on and so on and so on. And this would have been kind of silly to write up by hand. I mean, this isn't too bad, but since it is the same stuff over and over again, we might as well take advantage of it. Similarly, since we're going to declare the same structure for each of those, I will just loop over those registers and instantiate a register for each one. So in this case, I need a name, an instance name that is different than a signal name because they live in the same namespace, and so they will collide. And so, quote d.r concatenates the register name with the string d. So now all of my registers are going to be dpc, dt, dtrd, dz. And so this makes it really easy to figure out, a relationship between flip-flops and signals when you do this sort of D signal name. And they're all the same D flip-flop, but that was procedurally inferred. So that's that one. So this is another trick, just iterating in a loop, and it's the same loop we did before. The / semicolon just gets us around that. And then the last one, these sort of block assignments where you're doing the same thing over and over again. In this case, all of the inputs of all the registers are on the same bus. So the bus fans, there's a main bus that fans out to all of the inputs of the registers if they happen to be bus attached. And so this is just an assignment straight across. So we could go, so this is, yeah, so it turns out there were only 3 that did that. Maybe there were more. Some things we didn't write out because they have some interesting behavior, but we have an instruction decoder, and so it's way easier to go into our op table and look up what the op's going to be doing that. And so this is kind of one of the last design patterns that we'll do, is that oftentimes you have an arbitrary number of cases in a case statement, and so you can loop over table indexes. And in this case, I generated the microcode index for the op table. So I'm actually using the opcode to do that, and then the op name is kind of in a comment behind it, and that's what this $O is. So in this case, the op table, that is the pairs of op names to op codes. So this is going to be for each op name in op table. The op code is going to be a case in the case statement. So the op code and then the op code value if they match. The micro instruction pointer for instruction recoding is microcode index $0, and so this is going to return which microcode indice we go to for a specific op. And then we do the same thing a little bit lower, just a lot bigger, for the microcode control table. So depending on what part of the state machine we're in, certain control signals go high, and so we just record it out like this. And this is a lot easier for the tool to optimize when it's written this way, is that this literally gets stored as a huge lookup table and then evaluated using fairly standard logic optimizations. The sort of stuff that you'd learn freshman or sophomore year in Intro to Logic. So we've been talking for a bit, and then I don't think anybody's been watching, but in case, no, somebody's been watching, just no questions. And yeah, if you're the solo watcher and you're curious if you have any questions, I'd be happy to answer them. Otherwise, we will call this one done. All right. Maybe somebody's just using me to help them be productive. Some folks have told me that it is helpful to hear me talk in the background, that I am moderately soothing. So that'll be it for our intro to Perl. If there are other things that you'd be interested in learning about Perl, or something you'd be interested in seeing in Perl, feel free to let me know in the comments, and maybe we'll use one of our weekly design videos to kind of talk about that. Or if I owe more makeup lectures this term, we can do that there too. Have a great Tuesday, and I'll see you all next time.